This is 4.7, combining rules of probability. So we're not really adding much new here, but we kind of are. So the first example should be a familiar problem. You've actually solved this problem quite a few times on homework, on notes. We always did it with a tree diagram. So that's what I'm going to do. Okay, so first we're going to look at the tree diagram to answer this question. Okay, it says flipping 3 coins, find the probability of exactly 2 tails. So I'm just going to go on the side over here, give myself lots of space. First coin, heads or tails, right? And then remember, we always branch off from each of those options. Second coin, heads or tails from each possibility of the first, right? If I got heads on the first coin, I could still get heads or tails on the second. If I got tails on the first coin, I still could get heads or tails. And then branching off from each of those, for the third and final coin flip, we have heads or tails, heads or tails, heads or tails, heads or tails. And so we're going to actually get a lot more complicated. Okay, we're eventually going to flip 14 coins asking for certain values. Okay, so we don't want to do tree diagrams every time because that's going to get quite annoying. I spelled that wrong, I just noticed. There we go, tree diagram. But this is how we have been doing it. So I have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. Some of you probably have this memorized. I'm looking for exactly 2 tails. So heads, heads, heads. Nope. Heads, heads, tails. It only has 1 tails. Heads, tails, heads. Nope. Heads, tails, tails. There we go. There's 1. Heads, tails, tails. 2 tails right there. Tails, heads, heads. Nope. Tails, heads, tails. Oh, there's another one. Tails, tails, heads. There's another one. And tails, tails, tails. Well, that's actually 3, but I want exactly 2, so that's too many. So 3 out of 8 is my answer. Okay, like I said, some of you have been doing this, and you probably have that answer memorized. You can just write it. Okay, but we're going to make it easier. You don't have to draw a tree diagram to answer these questions. So what if we flip 3 coins and want exactly 2 tails? Well, I have 3 coins, so I have 3 categories. I'm not writing the equal sign yet, you'll see why. Each coin flip, I want exactly 2 tails. So I want 2 tails. Well, if I want 2 tails, that means the third coin must be heads, right? Because that's 2 tails. So I think about, okay, what's the probability of getting tails on that first coin? 1/2. And the second coin, 1/2. And the third coin to get heads happens to also be 1/2, but be careful about that. Okay. But most of you are probably saying, well, what if I got a heads and then 2 tails? Hopefully you're thinking that, and that's true. So we have 3 coin flips, and we have 2 tails, and we want to find how many different ways we could get that. So we're going to multiply by 3C2, the combinations. Okay, so to type this in your calculator, you do 1 divided by 2 times 1 divided by 2 times 1 divided by 2 times 3, then use the NCR button, then 2, and then hit enter. And if you do it correctly, depending on your calculator, you'll get 3/8. Or if you are like most people and it comes out as a decimal, 3, let me find the decimal real quick, 3 divided by 8, there we go, 0.375. And we can, oops, I forgot the 7, 0.375. And we can move the decimal twice to the right and get the percentage because I like percentages. 37.5%, which is the same. It's 3/8. 37.5% is 3/8. So we got the same answer using combinations, though. Okay, and that's kind of nice because the next question, example 3, we roll a die 4 times. A die has 6 options, so I'd have 6 options. Then from each of those, branch off 6 times. And then from each of those, branch off 6 times. And then from each of those, branch off 6 times, which doesn't sound too bad until you actually calculate it. And it would be 1,296. I don't know about you, but I don't want to branch off 1,296 times. So this is one where I'm definitely going to start using that thing. So 4 times. So 1, 2, 3, 4, and then don't forget we'll have the combinations. Exactly 3 6s. So I want a 6. I want 3 6s. And then the last one, I want anything else. So I'm going to write not a 6. It can be any other number. It doesn't matter what number it is, as long as it is not a 6, because then I'll have exactly 3 6s. Well, 6 is easy on a die roll. It's 1 out of the 6 outcomes. Not 6, we got to think. Well, how many numbers are not a 6? 1, 2, 3, 4, 5. So 5 out of 6 times the number of combinations. So our combinations, really you take the bigger numbers, the n, smaller numbers, the r every time. But I have 4 dice rolls and I want 3 6s. So 4C3. That is how we find the number of combinations. So you type that in your calculator, 1 divided by 6 times 1 divided by 6 times 1 divided by 6 times 5 divided by 6 times 4, NCR 3. Test this, try this. Make sure you can get this correct. And you get 0.015. It's a really small probability, actually. 1.5%. If you've ever played the game like Yahtzee or Risk or something like that, getting 3 6s does not happen very often with 4 dice. Okay? So example 4, roll 4 dice. Find the probability of exactly 4 5s. So 1, 2, 3, 4. So this one's easy. I want 5s every time. I want all 5s. It's a 1/6 chance to get a 5. Right? One of the 6 outcomes is a 5 times 4C4. If you type in 4C4, you'll notice that the answer is 1. Okay, that is because there's only one way in 4 dice rolls to get 4 5s, and that has to be every single one getting a 5. You can't reorder them, right? Because they're all 5s. They're always all 5s. So it does end up being 4C4. This is a question we've actually already answered before we learned about combinations and how to use that. But now you can use combinations and still get the exact same answer. Okay, so it's really small. Probably should have actually changed this question because it is a really small answer. And then we move it twice to the right, and you get 0.08%. Really small probability. Okay. So we get to our hardware store questions. A little more complicated now, though. So a hardware store has 3 out of 15 defective drills. Find these different probabilities. The next 2 sold are defective. So I have 2 drills being sold. It will change as we sell them, so that's important to take into account. And I want them both to be defective. Okay, so 3 out of the 15 are defective, times I'm selling a drill, so a defective drill is gone, or we assume we succeeded. So I only have 2 out of 14 next, times the number of combinations now. We already answered this question, so you're probably thinking, well, we didn't use combinations before, but that's because I want all of them to be defective, 2C2. Meaning I'm selling 2 drills and I want them both to be defective. If you type that in, you get 1. There's only one way to do this. They both have to be defective. That's why before combinations it still worked, but now you know combinations for it to work. And I'm just going to go straight to the percentage, move the decimal twice to the right. Don't forget how to do that. 2.9%. Done. Okay. But now we're going to make it more complicated. What if I want the first 2? I'm going to sell 3 drills. So we're going back to the original problem. Don't continue it. Always go back to the original problem. Now it's asking, well, what if I sold 3 drills, 2 non-defective and 1 defective? So not defective, and defective. But notice there are different ways. I could have sold 2 not defective and a defective, or I could have sold the defective first and then 2 not defective, or I could have sold not defective, then not defective. So this is where combinations becomes important. So we got to think. I'm going to sell a drill each time. Remember, we're assuming we were successful with what we wanted. So not defective. I have 12 out of 15. There are 12 drills that are not defective out of the 15. I have now sold a non-defective drill. That means I only have 11 non-defective drills left out of a total 14. Now I've sold 2 non-defective drills, so most people can get that part. But think, I've sold 2 non-defective. How many defective do I have left? If I had started with 3 and I just sold non-defective ones, I still have 3 left. And we need the combinations. So I'm selling 3 drills. I want 2 of them to be not defective or one of them to be defective, it actually doesn't matter which number you pick. It could be 3C2 or 3C1, and it actually will give you the same answer. Okay, but remember that 3 is the total number we're dealing with. We have 3 drills, that's why that one has to be 3. So once again, I'm going to jump right to the answer. So when you multiply and you get 43.5%, move that decimal twice to the right to get the percentage. And last one of this section, it says 4 out of the next 5 are not defective. So remember, we're going back to the original once again. We're selling 5 drills this time. So 1, 2, 3, 4, 5. I want 4 of them to be not defective. The last one to be defective. Okay, so we already know, well, am I not defective? I have 12 out of 15, right? 3 of them are defective, that means 12 of them aren't. And then I've sold a non-defective, so now I only have 11 out of 14. I've sold another non-defective, 10 out of 13. Sold another non-defective, 9 out of 12. And now I'm going to sell a defective. So I only have 11 drills. I've sold 4 drills off, so I went from 15 to 11. But the number of defective drills stayed the same because I was selling non-defective drills every time. Okay, so then we have 5 drills total, C4. Remember that bigger number is always first. Total number of drills we sold. 4 is how many non-defective we want. Or you could do 5C1, how many defective, would give you the same answer either way. And you get 49.5%. Okay. Example 6, 5 dice are rolled. What is the probability of getting exactly 3 2s? 2, 3, 4, 5. And I have the combinations to do this. So I want 3 2s. So I want 2, 2, 2, not 2, not 2. Those are the probabilities I'm looking for. This time it's it's not changing, right? With the hardware store, as we sold drills, we had to pay attention to what the new probability was. Dice rolls, you don't have that. Every time you have 6 outcomes. So 1 out of 6 are for 2. Not 2, so it's a 1, 3, 4, 5, 6. There's 5 of them that are not 2s. Times our number of combinations. So I have 5 dice rolls, so that's 5. The number of fractions should be that first number. C, 3. Because I'm rolling 3 2s. That's what I want. Okay. So type it in. Move the decimal, 3.2%. Then we get to a table. So now we have a lot of things to deal with this table. This is actually the same table as the last set of notes. So I'm going to fill these in really quick. The totals. Remember, this box is the grand total. And they should both add up to that grand total, which they do. This adds up to 180. This one adds up to 180. So my grand total is 180. That is the grand total number of people we're dealing with. So the first question, if I took one student out of the whole thing, what is the probability they will be advanced math? Okay. So advanced math is 50 out of the 180 total students. And just to make things easier, I'm actually going to find the percentage this time. Okay, so we get 27.8%, rounding to the nearest tenth of a percent. Okay, then we get to conditional. So you can't forget about conditional probabilities. Remember, this means we read it given. So probability of stats given transfer students. So that means we only have transfer students, right? Fraction line, I'm only dealing with the 45 transfer students. How many of those transfer students are in stats? 20 of them. So if I took only the transfer students, what's the probability of getting a stats student? That is also a transfer. It's 20 divided by 45. So type that in your calculator and you get 44.4%. Okay, remember, conditional probability changes what you're looking at. So now I'm looking at advanced math, given what's the probability of transfer given advanced math students. So I'm only dealing with advanced math students. So I have 50 total. How many of those are transfer students? 10. So I would go on my calculator, 10 divided by 50, and I get 20%, exactly 20%. That's why I don't have a decimal there. Okay, now we have an and. So we normally would multiply things, which you actually can. You have to use the multiplication rule. So you assume the first one. So stats, you just find the probability times non-transfer. It's given the stats, and it gets a little complicated. One nice thing about these tables is we actually don't have to multiply. Think about it. Logically, think about it. This is asking how many students, what's the probability of getting a student that is both a stats student and a non-transfer student? So we're looking at the total. There's no condition, so it's out of 180. If there's no condition, we always compare it to the total, so over 180. The only time that changes is with that line, the condition, the given. This one doesn't have a line, so it's all of them. So what's the probability of being a stats and non-transfer? Well, look at it. Stats, non-transfer. Right here. That number are the number of students that are both stats and non-transfer. So instead of having to do some complicated multiplication, I know 70 of them are stats students that are non-transfers. And so I just type that in, 70 divided by 180, and I get 38.9%. Done. So we'll do another one, advanced math and transfer. Once again, no condition, so we have to have the whole group. Advanced math and transfer. So advanced math and transfer, I have 10 students that meet both conditions. So I would divide 10 divided by 180, and I get pretty small actually, 5.6%. Okay. Now we have or. Okay, or, the next two problems actually are both or. Or doesn't get easier. This has to be the addition rule every time. Where the multiplication stuff, because of the table, how it works out, you can actually pick it out instead of having to multiply anything. Addition, you can't. So we got to do probability of stats plus the probability of transfer minus the probability of both stats and transfer. And notice we have that and within it. So we got to think about the and to be able to answer the or. It's more complicated, takes a little more work, not quite as easy, unfortunately. So first, probability of stats. So out of the 180 students, how many of them are in stats? 90. Plus probability of transfer. So out of the 180, how many of them are a transfer student? 45. Minus the probability of stats and transfer. So it's still out of the total, 180. But how many students are both stats and transfer? Stats and transfer, I have 20. That's where they meet up. So 20 students are both. Okay, so then we add and subtract. Just use your calculator, 90 divided by 80 plus 45 divided by 180 minus 20 divided by 180. And move the decimal twice to the right, 63.9%. Remember, the ors usually give you larger ones, the ands usually give you smaller ones. Okay. Probability of AP Calc plus the probability of stats minus the probability of AP Calc and stats. It's or again, so we have that. Probability of AP Calc, well, out of 180, right? Looking at the total group, how many AP Calc? 40. Plus, probability of stats, okay? How many total stats? 90. Minus the probability of both. So out of 180, how many students are in both AP Calculus and Statistics? Well, they don't overlap at all. So that tells us something. Can a student be in both AP Calculus and Statistics? No, so 0. There's no students in both. These are called mutually exclusive events. That should ring a bell. They cannot occur at the same time. I can't be a student in both AP Calculus and Statistics. So you'd actually type that in now. You just have to really add the first two because the second one is 0. So type it in. 40 divided by 180. Plus 90 divided by 180. If you want to hit minus 0, you can, but you don't really have to. And remember, move the decimal twice to the right, and you get 72.2%. Once again, the ors end up with pretty large probabilities compared to the ands. Notice how the ands are pretty small, nothing over really 50%. The ors are usually a little bit larger. Okay, so with that, write your 3-sentence summary.